Alright, hi guys, and welcome to a brand new PSP tutorial. And in this tutorial, we're going to go ahead and start off doing some basic things here with sort of this embedded graphics, or as you would call it, Framebuffer graphics. This tutorial is going to be structured a little bit differently. I'm going to go through the general theory of how you're going to go ahead and approach the problem. And then I'll go ahead and do implementations. In this case, I'll start with Zig, and then C and C++, and then Rust for this tutorial. So for the general theory of this sort of tutorial, basically we need to take a mile away look at the problem. What we want to do is draw 2D graphics onto a screen. So in order to do that, let's take a very quick look at what a screen is. So basically a screen is composed of pixels. On the PSP, it's 480 pixels by 272 pixels. And all of the colors of these pixels are determined by 4 bytes, which is R, G, B, and A, so red, green, blue, and alpha. And these components basically make up each pixel in the frame buffer. And the frame buffer is just a big list, or a big array, as you could represent it, of different entries. So knowing this, on the PSP itself, the frame buffer is stored in video memory, which kind of makes sense. It's all about videos, right? And graphics. So which starts at the address 0x0 400 0000. That's a pretty big number, but basically that's where our frame buffer address is in RAM. The frame buffer itself actually contains 32 more pixels on the width side, and that's actually due to fulfilling a power of 2 rule for the size of the frame buffer. So therefore the actual frame buffer is 512 pixels by 272 pixels. Now, a pixel is represented by the 4 colors, right? Each color has an optional length, depending on what your frame buffer mode is. By default, it's RGB A8888, which means 8 bits per each single one. So R is a value from 0 to 255, and it describes how red the pixel is. Same thing with green and blue. So knowing this, since that's 8 bits times 4, that's 32 bits. So it's a 512 by 272 buffer of unsigned 32 bits. So in order to go ahead and draw to the screen, what we actually want to go ahead and do is basically we would take whatever the thing in the buffer is, and we would go ahead and set up that buffer, and we would go and basically just write the pixel values directly. That's called software rendering, and that is probably the simplest and easiest solution for rendering. It is also very inefficient because we're rendering on the CPU itself. The GPU would be so much faster, but in this case it's very simple and easy to understand. So basically, if we want to draw things onto the screen, we'll have to draw it pixel by pixel across the entire buffer. For a renderer, we'll also be implementing something called double buffering, because on single buffering means that basically everything is just a raw draw to the frame buffer, and there's no intermediary. And what that actually results in is a lot of flickering. And flickering is actually a pretty bad graphical thing to see on the screen. So in this case, we're going to actually have to use a second buffer, draw to that buffer, then swap the frame buffers essentially, and start drawing to the new buffer, and the other one gets displayed to the screen. That way you don't get that awful screen tearing as things render onto the screen. The other thing that we'll be doing is going to be implementing methods to draw rectangles to the screen as the basics for what our frame buffer renderer here is going to do. With that sort of general theory, we can go ahead and create a module in Zig for that. And let's go ahead and get started with the Zig portion of the tutorial. Alright, so to create a new sort of module for Zig, we're just going to create another file and call it graphics.zig, so gfx.zig. In this file, we're going to need a few prerequisites here. So the first thing I'm going to do is do using namespace for an import of Zig PSP source PSP include PSP GE. I'm going to need, probably, I think I need PSP utils, and then PSP display. And I'm going to, of course, use my zig PSP /source /PSP include, or sorry, utils /PSP.zig. Not sure exactly if I need all of these, but I believe that should be enough. So next thing I'm going to create is var draw buffer. So this is the buffer that we're actually going to be using to draw to the screen. In this case, I'm going to use a question mark, which is an optional pointer to U32 array, and we're just going to set it to null for now. Same thing with the display buffer, which is going to be disp buffer, and it's going to be the same sort of setup here. Cool. So the next thing that we're going to do is actually create the initialization method. So to initialize here, we're going to do pub function init, which is type void, and then we have draw buffer is equal to an int to pointer, and then we're going to do question mark 32, right? So that's our normal sort of buffer pointer that we have already, and we're going to do a pointer to int SCE GE EDRAM get address. Now this is what actually gets the frame pointer. So that's going to be the 0x number there. And the reason that I'm using pointer to int here and int to pointer is because of what I'm going to do with the next one, which is the display buffer is equal to the same thing here. So copy that. But once it's turned into an integer, we're going to add 272 times the screen buffer width, which is a constant. This constant actually evaluates to 512, so 272 by 512 is our array there. And then we're going to multiply by 4 because it's 4 bytes per this array. So we're just going to go ahead and add that to our buffer. That way we now have two buffers that are basically side by side in memory that we can draw to. Next thing we're going to do is underscore is equal to SCE display set mode 0 to screen width and screen height. I'm actually referencing constants from utils psp.zig, but in this case I'll specify what they are for people. So screen width is 480 and height is 272, and then we're also going to set display set frame buffer to the display buffer. So display frame buffer is the display buffer. So then we're going to set the screen buffer width, which is 512, and then we're going to do the enum to int for PSP display pixel formats, and we're going to choose format 888, which is the RGBA 8888 format. 8888, yes. Okay. And that's how we're going to go ahead and set up our initial frame buffer. Now, like I said, I was talking about how we're going to do swapping frame buffers. So in this case, to swap a frame buffer, what we're going to do is create a function for swap buffers. And in this case, it's going to be void. And all that we're going to do is create a temporary buffer. So var temp is equivalent to display buffer. Then display buffer is equal to draw buffer, and draw buffer is equal to temp. Now this is the most basic way you can do any sort of swap of two variables, and that's pretty much what we've just done here. Next thing we do is going to be a quick thing here. We're going to kernel dcache write back invalidate all, and invalidate all. And what this does is it clears our data cache. So currently, when you're writing to your draw buffer, you're actually writing into CPU memory cache, and that isn't necessarily synchronized to what actual memory is. So before we go ahead and set up all the buffers, set the new buffer, we're going to make sure that we have gone through and written back all of that data back onto the actual memory. That way we can be sure that when we set the memory that the screen is going to look correct. So that's the reason why we're doing that. And then the next thing that we're going to do is a repeat call here to SCE display set frame buffer. And we can do the same thing right here. Now, the second enum here is actually PSP display set buffer sync to the next frame. This can be done with PSP display set buff sync display set buff sync dot next frame as the type that we're going to be using there to set it. There we go. And that means on the next time that the frame, the next frame that goes ahead, that it will be basically drawn onto the screen. That way it's not immediately trying to overwrite. And that's the reason why we did that. So the final and next thing that we're doing is we're going to create, well, not the final thing. The next thing that we're doing is creating the clear method, which takes in the color, which is of type U32, because as I said, RGBA 8888 is 4 U8s strapped together for RGBA. Since we're using little endian, it's actually ABGR. And what that means is that if you actually wrote it R and then G and then B and then A, yeah, it would look correctly if you were doing it as U8s. But if you do it as a U32, it's actually represented in the opposite format. And that's just one thing that you need to keep in mind. So here we're doing a variable I, usize is 0, and while I is less than the buffer width, which is 512, times the height, which is 272. Then we're going to go through each and every index, I plus equals 1, and all we're going to do is go ahead and set draw buffer dot question mark, because we have to discard the null check here, and this actually does a null check for us anyways, and won't let us permit if that was the case. Oh, what was that? That was strange. And then dot question mark, and now we just have a raw array pointer, and then we use the array to point to I, and then set that equal to the current color. And that's that. That's all you need to do to actually set up the clear method. The clear method is very, very simple in this case. So finally, the last thing that we have to do, which is our rectangle drawing method, is going to be pub function draw rectangle. We're going to take an X of type usize, Y of type usize, W usize, height usize, and then color, which is U32, and set that equal to void. So next thing that we're going to do is actually pretty simple. We're going to create a mutable version of everything. So y0 equals y, var w0 equals w, and var h0 equals h. We have no need to change color. And the reason we have to do this is because these values in the call are actually constants. They will not be able to be changed unless they were, for example, if they were a pointer, then yeah, it would be passed by reference. In this case, it's actually just a pass by value, and those values are by default immutable. So that's why we need to do that. And what I'm going to do next is do if x0 is greater than 480. So if it's greater than 480, we can't actually go past that. So if our starting point is 480, we can't do anything past that. So x0 is 480. For example, if y0, for example, is greater than 272, well, y has to be y0 has to equal 272. Pretty much, the next thing that we would do is if our x0 plus our w0, so if your x plus your width is greater than 480, then we can't overwrite the buffer there. We actually have to go ahead and recalculate what w is. So w0 is going to be, so w0 would be 480 minus minus the current x value, so minus x0, and that's the maximum number of pixels that you can actually draw on the screen. Same thing here is going to happen with y0, so if y0 plus h0 is greater than 272, then h0 has to be 272 minus y0. Now that we've done all those logical checks, we can actually go ahead and calculate where we need to be on the screen. So what I'm going to do is calculate the offset. So the offset currently, which is a U size, again, is x0 plus y0 times the screen buffer width. And this way we can find where we are supposed to be inside of our entire frame buffer. Finally, we'll create y1, which is a U size, 0, and then say while y1 is less than h is 0, then h is 0, or sorry, y1 plus equals 1. Then inside here, we'll create var x1 of type usize is 0, while x1 is less than w0, x1 plus equals 1. And then finally, we'll set up inside here, draw buffer, dot question mark, x1 plus the offset, plus y1 times the screen buffer width, so times 512. And what that does is we say wherever we are on the x plus the offset, plus wherever we are on the y. And then we set that equal to the current color. And that way, we now have a method which safely and securely draws a rectangle onto our screen and makes sure that we don't overrun the buffer. So now that we have that, we can go to our main.zig file here, and we'll create a const graphics is equal to import graphics.zig. And what we have to do here, instead of screen init, we're actually going to do gfx.init and do that. And the next thing that we would do is then we would probably want to do graphics.clear, and now we can set up whatever the color is. If you're familiar with CSS and RGB sort of codes, so like hash 082 CAFF, which is the sky blue, and that's RGB. If we added a second FF here, RGBA, it needs to be reversed on MIPS, so 0xFFFFCA82 would be the equivalent. So in this case, to write it, it's 0xFFFFCA82 as the reversed version. That's just to get the part done. We actually probably should make this a loop. Of course, we'll do while true. So an infinite loop, which does graphics clear. So we want to clear at the beginning of every frame. Then we're going to do graphics.drawRect, since we created the method. We're going to do it at 10, 10, and then have a size of 30 by 30, and the color should be yellow, so 0xFF00FFFF, which is red is max and green is max, which draws yellow. And then we're going to do graphics.swapBuffers. And then the last part we're going to do is a discarded call here to underscore equals SCE display wait v blank start. I might need to check the capitalization of that, but we should be able to go ahead and do it in cpzig Zig build. Zig version 0. What have I done here? SE display wait v blank start. Probably misspelled it, or possibly I actually have to include display in here, so really quickly just gonna copy this over. There we go, using namespace. That should be enough. There we go. And if we go ahead and run eboot.ppp, sorry, that's actually not the way that you can run it. ppsspp, file, open directory, PSP tutorials, Zig, and then that should be good enough. So as we can see, PPSSPP shows our results here with our clear sky blue sky and our nice little blocky sun in the top left hand corner. All of the coordinates in the system start from 0, 0 at the top left and go to 482, 72, which is the bottom right. X goes across this way and Y goes across this way. Congratulations on your tutorial, and I hope to see some pretty cool looking PSP applications drawn with some nice colorful rectangles. Alright, so let's go ahead and get started with the C and C++ version of this tutorial. And I'm going to be doing them kind of at the same time, mainly because they are very, very similar with a very small differences, and I figured that doing it twice, once for C and once for C++, is actually going to take me a lot more time than necessarily is needed for this tutorial, and I'd rather not have an over an hour long recording, and if not an over an hour long tutorial. The principal difference between C and C++ in this application is going to be the use of namespaces as a cleaner alternative to GFX underscore in C. So the very first thing that we're going to go ahead and get started with here in C is we're going to create a new file, and this is going to be our gfx.h. So this is the header file for our graphics library. In this header file, all we want to really go ahead and do is define a few functions here. Void gfx underscore init, void clear, gfx underscore clear, and this one's going to take a uint 32t color, and then we'd also want we need by the way, we would need an include stdint if we're in C, sorry, stdint.h, which is that uint32 underscore t color, and then we're going to go ahead and also add void gfx swap buffers. We could also write it out as swap underscore buffers. Either way, does the same exact job. And then void gfx underscore draw rect as a rectangle, and then we're going to do int x, int y, int z, w, int h, and then uint32 underscore t for color. And that way we now have our entire graphics API sort of detailed in C. Now to denote what it's going to be like in C++ is we're going to create gfx.h, or hpp if you want for C++. They pretty much fulfill the same exact thing, except in here we're going to be using cstdint, of course, because it's C++. Next thing we're going to do is create a namespace called gfx, and then we're going to change about the naming convention a little bit too. So we're going to go, we're going to go ahead here and pretty much, hello, there we go. And then we're going to pretty much say gfx, capital I, init, clear, swap, buffers, draw, rect. We could also do it with lowercase, which actually I'm going to prefer here for C++, because C++ typically uses camel case. So in this case, now we have the same exact sort of definition here for graphics.hpp and graphics.h. It's basically the same thing, just with a little variance. So for C, we're going to go gfx.c, not comma C, dot C. There we go. Which is going to go ahead and hashtag include gfx.h. And in order to include gfx.h, then we're going to go ahead and take a look at all these different methods. We can pretty much copy them over, and then go ahead and define every single one of these functions. So we create the actual definitions here. Cool. And let's just keep them in the order that we have them here. The difference here for gfx.cpp is going to be that we're using the namespaces once again. So we're going to hashtag include gfx.hpp, and then we create namespace gfx, and then we're pretty much going to take gfx.hpp and take all of these methods and pretty much just do the exact same thing that we just did in C, except now we're doing it inside of a protected namespace. And this actually comes in handy a lot. Protected namespaces are something nice inside of C++, mainly because it actually allows you to not run into issues where you would have some sort of collision, namespace collision. So, for example, if we didn't prefix this with gfx underscore, and we just did init, and we have another thing that does init as well, these two symbols will clash, and it will cause issues. C++, now that they're in namespaces, it's 100% fine to have clashing things, because you're going to refer to them as gfx init. And that's pretty much the way that you can go ahead and sort them out. It's very much a personal preference thing, and I know that a lot of C and C++ programmers are going to argue for days on end about whether or not which one is better. But in my personal opinion, it's a lot easier and nicer to read and write code with gfx init. Of course, I am a fan of Zig, which very much does the same exact sort of logic here. So, you know, just call it as it is. So pretty much what we're going to do in gfx.cpp and gfx.c are going to be basically identical. So the first things we need to do is we're going to actually have to declare a few variables here. And what we want to go ahead and create is we're going to create pointers. And these pointers are going to be uint32_t pointers. And they're going to be pointers to our draw buffer. And we're going to do the same thing for our display buffer. That's pretty much all that we need for that. The next thing that we're going to do is actually we need hashtag include pspge.h, and we're going to go ahead and say draw buffer is equivalent to edram get address. Same thing here for display buffer, except we're going to go ahead and add onto that, since we can just do direct pointer arithmetic, 272 times 512, which is the screen height times the screen width. So that's the size there. But since we're referring to it in bytes, we're doing size of uint32_t, which, by the way, shortens out to be 4. So that way we can go ahead and do that direct arithmetic. Let's see what the issue is here. Get the EDRMRS. Expression must be a pointer to a complete object type. Oh, so we're going to actually have to make a cast here. So uint32_t pointer. Give that a second to resolve, and there we go. That fixes our small issue there. Next thing we want to do is actually include display. So hashtag include PSP display.h. And inside of this, what we're going to do is sce display set mode 0, then the screen width and the screen height. So we're going to be 480 by 272, and sce display set frame buffer, and this is going to be set to the display buffer, which is going to be the void pointer there, integer for a buffer width. So the buffer width is actually 512, it's power of 2. Next thing is going to be PSP display pixel format 8888. And then we're going to use sync as next frame, which is 1. Next thing we can do here is do a for loop, and I is 0, I is less than 512 times 272, and then I plus, and then inside of here we're going to do a draw buffer at I is equal to the current color. Let's see, there we go, color. And that's pretty much going to be the entire method to clear the entire screen. It's pretty simple. We iterate through every single available pixel and we set it to the color. The next thing here that we're going to do is we're going to go ahead and implement our swap buffers call. And our swap buffers call is pretty simple. All we're going to essentially do is do uint, wow, I can't spell, uint32t underscore pointer temp. Uint 32 underscore t pointer temp is equivalent to the display buffer. The display buffer is equal to the draw buffer, and the draw buffer is equal to the temp. And that is pretty much the most basic way of swapping something in C or C++. I'm also going to go ahead and include PSP utility.h, I believe, or utils actually.h. There we go. That's what I wanted. PSP utils.h, and we're going to do SCE kernel dcache write back invalidate all. And what this does is it clears the data cache. And why is that important? Because after we've gone ahead and written to our buffer here, we've written and overwritten things. This is writing to the cache directly. And if we don't synchronize the cache before we go ahead and do something with things that are potentially written and floating around in cache, we might actually encounter some strange looking corruption if we didn't actually set back that memory. So this is what sets back the written memory that hasn't necessarily been saved to the main RAM or the VRAM yet. And this forces that to happen. Then we're going to go ahead and do display set frame buffer to display buffer again, 512, and then PSP display pixel format as format 8888. There we go. And PSP display set buffer as the next available frame. And that way we can go ahead and swap buffers. Final thing here is going to be what we do to draw a rectangle onto the screen. So we want to do this safely. So we want to make sure that we're not overrunning where our buffer is. So if x is greater than 480, we have to say x is equal to 480. Same check goes ahead and applies if we wanted to do the same thing to y here. So if y is greater than 480 and y is equal to 480, so if y is greater than 480, it is equal to 480. One thing I should have done here is actually specify that you need to specify an unsigned integer, and this way it's actually probably clearer and better if we use unsigned ints than we use the signed ints, because this way we can guarantee that it's never going to be less than 0 and we don't have to check for that. So I'm going to go ahead and briefly just update that in the locations here. And that's actually just to be more safe about the way that we're using our types. Alright, so now we have unsigned integers everywhere. So in order to draw the rectangle, yes, we check for x and we check for y. The next thing that we need to do is check if x plus the width is going to be greater than 480. Then we actually have to set width is equal to 480 minus x. That way we can get the exact number of things that we have to draw. This helps you save out on some cycles and prevents buffer overwriting as well. Same thing here with y plus h. We're going to say h is 272, actually minus y. Should have used 272 here. There we go. And that way now we are safe for what we need to go ahead and write. Once again, we're going to create a integer offset, which is x0 plus, which is x, I'm thinking in Zig, plus y times the current screen buffer width, which is 512. Now for this, we're going to do for int x1, or actually y1, sorry, integer y1. We want to be writing concurrently, so y1 equals 0, y1 is less than our total number of height, so y1 less than height and y1 plus plus. Then we'll do the same thing here, nested for x1 is 0, x1 is less than width, and x1 plus plus. Then we can go ahead and write to our draw buffer at our x1 location plus the offset that we already have plus the y1 location times the screen buffer width. And that way we can then go ahead and set our pixels there to our current color. Let's go ahead and see that. It resolves, and that is how we go ahead and draw to the screen. So let's go ahead and go into our main.c here, which I'm going to clean up just a little bit here for stuff like this. We don't actually need PSP debug screen in it for this either. And we're going to go ahead and do hashtag include graphics.h. We'll call graphics in it. And then we'll call a while loop here, while true, graphics clear. And then we're going to go ahead and set a color. If you know how RGBA codes work, true actually doesn't work here, so while 1. So if you know how RGBA codes work in HTML, so for example, 0 or hash C82 CAFFFF is RGBA in hex. For the PSP, it's pretty much just the reverse order, so 0xFFFFCA82 in this case, and that way we can go ahead and draw our things properly. This is just due to the way that little endian works in this circumstance. So 0xFFFFCA82. We're also going to do graphics, draw rectangle. And what we want to draw a rectangle here is going to be at 1010, size of 30 for each, and then color, let's do yellow as our color that we're going to set here. Am I missing something? No, I am not. Okay. And then GFX swap buffers, and then one function call that we actually need here, which is going to be hashtag include PSP display.h is going to be SCE display wait v blank start, and that way we will have correct updating as our timings here. And to go ahead and build graphics.c, we're going to go into our make file here, add a backslash here, and just do gfx.o. And that way we can go ahead and add another thing here. We call make. It should go ahead and make our new files here. Great. Yep, and it's added up. We're going to go ahead and do ppsspp. File, open a directory. Let's go out here. There we go. PSP tutorials. Then we're going to do it in C. Open that up. And we should get nice little blue sky drawn here with the sun in the top left corner. So 00 is the top left corner, 482.72 is the bottom right corner, and pretty much this way is increasing x, so 0 to 480, and this is increasing y, so 0 to 272. And that's how your coordinate system works here. So there you go, that's the way that you do it in C. I'm going to go ahead and do the C++ version really quickly here. C++ version. And I'll do the C++ version here. gfx.o. It needs to be added here for C++. And pretty much everything inside of gfx.c is basically the same thing that's going to be written in C++. In this case, gfx.c++, we're going to create this inside of here. And then we're also going to go ahead and pretty much take all the same code from the gfx underscore methods and apply them to our gfx C++ methods really quickly. And I know that we are missing a few things here. We need the includes, if I am correct. Yeah, we need these includes to also be included inside of this file for that to be able to make sense. Let's see here. Type of void pointer. All right, so in C++, we're actually going to use static cast here as a much nicer way of dealing with our casting issues here. Wait for that to update. Yeah, and that is a much cleaner and nicer looking way, or maybe not as nice, depending on your viewpoint here, of what we should be doing. Now, I still think that we need to, oops, this should go here, and then add to it. There we go. That's what I wanted. So we need to go ahead and static cast this, and then add to it. That way we have nice type safety. Next thing we're going to do is go ahead and implement the clear method. Clear method is quite literally the same thing. Same thing here with the graphics swap buffers. And then the next part here is going to be GFX draw a rectangle. And we're just going to take that, throw it in here. And then we should be good to tap it over and manually fix that. So instead of what we do in our main.cpp file or C file where we do this, we're pretty much going to take the same exact concept, except we're going to go ahead and go into CPP here. We're going to go ahead and replace that with this, and then we're going to use : instead of our underscores, and that's going to help out with our interpretation here. Instead of underscores, it's also rectangle, so that's also true. And then we're going to go ahead and fix our dependencies here by hashtag include PSP display.h, and then we're also going to hashtag include PSP graphics.hpp. And that should resolve all of our issues here. And then we're going to go ahead and go out here, cd C++, and then call make on it, and it should generate the same thing. If we go ahead and take a look here at ppsspp, file, open directory, and then go into PSP tutorials and C++. There we go. We got the same exact sort of thing here with very much a similar implementation. Just using namespaces instead of all of the GFX underscore and things like that. So with that said, that's the end of the C and C++ tutorials for the PSP Framebuffer graphics. Alright, hello and welcome to the Rust section of the tutorial here. And what we're going to be doing is we're going to go ahead and take a look at how we're going to go ahead and do this in Rust. So to go ahead and get started, we're going to first create a new file here called gfx.rs, and this is what's going to be the main module for everything else that we're doing. We're also going to denote it as a module here using mod gfx. Right, so let's go ahead and get started with gfx.rs itself. So at the top, we're going to go ahead and use a few things here inside of the PSP crate. We're going to use sys display mode, display pixel format, and display set buffer sync, all of which are going to be required in this instance. We're also going to create a sort of object for everything, so renderer. So there can only be one renderer in your scene or in your program. So it's going to have the property of the display, the draw buffer, which is immutable U32, and a display buffer, which is also a mutable U32. Then we'll go ahead and implement some functions for the renderer to actually use. So for example, one of these is going to be the actual construction. And in this case, this takes the role of init in other languages. So pub unsafe function new, which returns a self. So it returns the renderer itself. So we're going to create a draw buffer, which is PSP, this SCEGEEDRAM get address. And for this one, it's actually going to be as a mutable U32. Same thing is going to happen with the display buffer. So disp buffer. But in this case, we want to go ahead and add on to it. So we're going to go ahead and add 512 times 272 times 4, which is the size of the first display buffer. So we're taking from the base. So we're taking from the base pointer of RAM and then adding our frame buffer to that, so that we get to the next available area for another frame buffer. Then we're going to go ahead and do PSP sys SCE display set mode with display mode, and then LCD. And then we'll also go ahead and set it to 480 by 272 as our screen display mode. Similarly, we'll do PSP system SCE display set frame buffer, and we'll do this on multiple lines here. First thing is going to be display buffer as a constant U8 pointer. And then we'll go ahead and do 512, which is our buffer width, followed by display pixel format, RGBA 8888, which is PSM 8888, and display set buffer sync, which is next frame mode. And finally, to fulfill the last requirement here, we're going to create an expression for self. That's just draw buffer and then display buffer. And there we go, that's our new method. We're going to go ahead and do pub function clear with a reference to ourself with color U32. So this is going to display our color, and it's pretty much an unsafe loop where we do for integer I in 0 to 512 times 272, which is the entire size of our buffer. We're going to do self dot draw buffer dot add I as u size, and then say equals color. Next thing will be the swap buffers call. So public function swap underscore buffers is going to be a mutable reference to itself. And in this case, we'll do a core memory swap, and we're going to use a mutable reference to self.displayBuffer and mutable reference to self.drawBuffer. Doesn't really matter the order here because it's going to go ahead and be set either way. And then inside here, we're going to do an unsafe PSP sys SCE kernel dcache write back invalidate all. And what that function does is it goes ahead and writes back all of the data cache, because when you're writing to memory, usually that's a cached memory access, and basically we need to flush that back to memory so that memory when it gets drawn to the screen isn't full of any corrupted or weird data. So that's why we do the dcache write back and validate all. And then we're going to go ahead and basically do the exact same thing here as this set frame buffer for call, except instead of disk buffer, it's self.disk buffer, which is the same. Great, and then we're going to go ahead and do public function draw rectangle, which is a reference to self. It's going to have x as a u size, y as a u size, width as a u size, and then width as a u size, and then height as a u size. U size. There we go. And then it's going to have color as its final element as a u32, And that's going to be that. Pretty much what's going to happen here is for every single y, so for y1 in 0 to height, and then for x1 in 0 to width, so we're going to go through that, if let sum pointer equals self.calculate, this is going to be another method that we're going to implement, calculate offset, then we're going to go ahead is equal to self.calculate offset of x plus x1 y plus y1. Then we're going to go ahead and do an unsafe dereference pointer is color. And in this case, we want to go ahead and make an inline function. So inline function, calculate offset is a reference to self with x as usize and y as a usize. And it's going to return an option with mutable u32 pointer inside. And then we can do unsafe if x is less than or equal to 480 and y is less than or equal to 272. Then we do one thing. Otherwise, we'll do the other thing, which is none. In this case, we want to do sum self.drawBuffer dot add x plus y times 512 as, actually, no, that's fine. It doesn't need to go ahead and make anything else there. So self.calculate offset is used here. So given that, now we should be able to go ahead and set up our main function here. So we're going to create an unsafe block here. We do let mutable renderer is equal to graphics renderer new. And then we're going to go ahead and do loop renderer.clear to our color here, which is going to be sky blue, which is 82 CAFF in RGB, and then we're going to go ahead and reverse that because we're on MIPS, which is little endian, so it's the opposite there. Then we're also going to do draw a rectangle, which is going to start at 10. Oh no. Which is going to start at 10, 10. That's going to be our XY, and then it's going to be 30 wide, 30 high. And then the color, we're going to go ahead and do as yellow. Then we'll do renderer.swap buffers, and then, swap buffers. And then PSP, system sys, SCE display, wait v blank start. And that waits for the next frame, so it can display the frame to the actual, that way we can display the actual frame to our PSP. So we'll go ahead and do cargo PSP here, which goes ahead and builds up like that. And then we can go ahead and do PPSSPP. And then we'll open up, actually here, let's go really quickly. Desktop, PSP tutorials, Rust, Target, Impsol, Sony PSP, and then this one. And then there you go. We have a nice little blue sky here with the sun in the top left corner. So that's your basics for drawing some nice little rectangles on the screen. I hope you have enjoyed the tutorial, and I hope to see some pretty cool creations that you make with this information. And that's going to be all that we have for today's tutorial. I hope you guys have enjoyed this tutorial. In the next one, we'll actually go ahead and look at a few other things relating to file, input and output, and other things like that in our various programming languages, including basically doing some work with standard library and C, C++, Zig, and then the experimental STD for Rust. Thank you guys for watching. Please like, comment, subscribe, and I'll see you guys in another video.